and welcome to Data Analysis with Python. My name is Kat, and I'll be teaching you all the ways that you can draw insights from data. So first, I wanted to very briefly talk about what data analysis is. In my opinion, data analysis is the process of collecting, cleaning, and interpreting data to uncover information and make better decisions based on that information. So an example of this in my job would be, here we have a list of data, right? And it's raw data. And then you can see at the top, we have the health status, which would be here, and whether or not a ticket has been opened. And all of this data helps us gather potential insights and understandings of how our devices are currently running and what we can do to make said devices run better. So with the more data that we have, the more insights we can draw about those pieces of data. But when you have a big data set, like the one we have here, that has, thousands of entries, it gets overwhelming pretty quick without automated tools like Python. So here, we're going to be turning raw data into insight with the help of Python. Unfortunately, you're going to need some basic skills with Python before you can start data analysis. So if I were you, I would start with a basic Python programming understanding. So that would include variables, different data types, control structures like for loops, if statements, while loops, the most basic things that you would use with Python. I would expect you to know those. I'll also expect you to understand how to work with lists, dictionaries, and functions, because oftentimes we use those when we do different forms of data analysis or go through multiple rounds of data analysis. Those are still, basic components of Python, but they're a little bit more advanced. I would also expect you to understand how to use libraries. In this situation, we're going to be using NumPy, Pandas, and Seaborn, which are all different forms of data analysis tools for Python. It's okay if you don't fully understand everything about a library, right? Libraries are generally pretty extensive, but I'm going to expect you to understand how to import them, how to reference them, and just generally what you need to do to use a library properly in Python. I'm also going to hope that you understand basic math components of data analysis. We're not really going to have time to go over why certain tools are used for data analysis or the thinking behind certain data analysis forms. So I'm going to say, hopefully you understand basic things like mean, median, mode, the difference between those, a basic data trend and how to look at it and evaluate it. And I'm also going to hope that you understand data cleaning. So if you have any data that's missing, you're going to take that into account when you do your data analysis. Or if you have duplicates, you're going to understand that that can cause issues. Basically, a basic understanding of what you'd need to do proper data analysis on a set of data. I think that's pretty much all that you'll need for this set of videos, but I'm going to say if you have any questions, I would probably try looking them up, or if it's something that I think we're going to be going over soon and might be a question, I'll be sure to let you know before we start getting into the topic. Basically, in summary, data analysis is all about finding the meaning in data, and Python helps you do it efficiently with tools like Pandas and Seaborn. Once you understand how you can manipulate and visualize data, you can really start discovering insights that help you solve real-world problems. So for me, data analysis has already been useful both here and previously when I was evaluating the way that learning assistants used our program at my college. So it was very helpful for me at that time, and I can say data analysis is one of the more important skills for someone who's looking to improve trends over time and maximize company profits and efficiency to the best of their ability. So as you can see, we're working with a web-based page called Jupyterlab. Now, Jupyterlab is the next iteration of what used to be called Jupyter Notebook. and it allows users to work with multiple notebooks, terminals, text editors, other things that can help you in the moment. So think of it as like a notebook with multiple pages, just like you would use in science or in math when you were in school, and it allows you to comprehensively keep track of all of the data that you're using with your data analysis here. It's kind of similar to a more complex IDE than idle. I wouldn't compare it to idle, but I would say something like your PyCharm. Basically, it's a project that allows you to group other projects together. And you can see here that it's web-based, and basically you have to start a server to get it up and running. So I'm going to go ahead and show you how to get it installed, but obviously I'm going to suggest, as always, that you reference the documents. So here, our documentation says to go ahead and use pip. If you don't already know, which I think you would based on the amount of Python knowledge that you're coming into this with, but pip is the native package installer that comes with Python, and you should have it unless you opted out of installing it and you know that you opted out of it. So I would try pip install Jupyterlab first. That's probably going to be your easiest method. And then from there, you're going to go ahead and launch Jupyterlab with Jupyter Space Lab. And here you can see I took a different approach, but that's because of the Python version that I have. So you can also run this command, Python tac-m Jupyterlab, and then you can see the process of it booting up. And it should either give you a, what would you like to open this program with? Or if that doesn't happen, or you're silly like me and you close it by accident, you can go ahead and copy paste either of these, not these ones, but whichever one it gives you when you run it. I would say that Jupyterlab is one of the more useful IDEs if you're doing data analysis because of the range that it has, and the environment that it's in is just constantly being updated. So now that we've got Jupyterlab fully installed and ready to go here, let's go ahead and talk about some housekeeping and how you can better use your Jupyterlab. To start, let's say that we want to look at two projects side by side, but not necessarily with two separate Jupyterlab windows or instances running at the same time. To do that, we could go ahead and hit File, New Launcher, or you can reference one of your old launchers if you want, using this File tab right here. And then we can open whatever we want. I'm going to go ahead and open a new Python, but what is really important here is I'm going to right-click and go to New View for Notebook. And now you can see that will split it. I went ahead and put it both in the first view and in the second view, but we can go ahead and close this now without any consequence, and then look at our Welcome to Data Analysis screen here, as well as our untitled one. So if we wanted to test something with this, we could test a basic print function, the old hello world, and run that here. And then just to prove to you that it can run both projects if need be, we can go ahead and say this is a test and run that, and there you go. Our test is working. So now that you understand how you could maybe view both of these at the same time, let's take a look at something that's very unique in Jupyterlab, but also very handy, and that is magic commands. So magic commands are a way to basically better understand your code and measure how your code is performing, as well as move throughout your working directory or the file paths that Jupyterlab has created for you with your project. So let's say that we wanted to look at the amount of time that a function takes. We can use the magic command time. The formatting for time is 2% signs. So if I go in here, whoop, and I put that in, and then I run it, you can see it didn't take any time at all to run, but it was estimating, or not estimating, it was timing the amount of time that that operation would take to run. And then I just accidentally collapsed this, so I'm going to go ahead and open it back up. But time is very useful if you are running a data analysis command and you need to know how long that command is taking, because there can be some really complex functions that you need to run, especially when you're considering AI and machine learning with massive data sets. You're going to want to know how long something is taking. Something else that's really handy is the write file command. So I'll show it to you here. It looks like this as usual, or as we've seen so far. It's got the 2% signs. And then the name of the command is write file. And we don't have a file that we're writing to right now, but you would put your file name here. And what that means is anything under it, okay, yeah, it complained about it, but anything under that item, that command, in the same cell, so in this section here, in that 2, that's a cell, anything in that cell will be written, the outputs of it will be written to a file. This is useful if you don't want to take the time, as I'm sure you know with Python basics, to import file IO and add to a file and then close it, or read or write, or anything that you would normally do. Instead of messing with that, you can just write whatever you have into a file. One of the more interesting ones that you have is who, or who ls. So like, let's say that we have a variable here that's just I, and we say I equals 10. And then we add a cell here. Well, let's try this. And we run this. Oh, okay, yeah. Sorry, it's upset because who in this case is 1% sign because it's not referencing any other variables. But we can see here, we've got percent who, and then it says interactive namespace is empty. So there aren't any variables that it can currently list for me, because the variables are variables that I've introduced to the namespace. So it would be a library that you're using, or in this case, I would show up as a variable in the namespace. But because I'm running it here and Python is top down, it hasn't found it yet. So let's go ahead and run it again here. So it says, oh, it still says interactive namespace is empty. Okay, so let's say that I wanted to capture the output of a cell. For example, we wanted to move it to a file elsewhere, or we wanted to reference it in another notebook. We could do that with the magic command capture, as the name suggests. So we go ahead and do %% capture. Now, this is another magic command that uses the double % sign, but that's not always true. Let's go ahead and take a look at one that uses a single % sign, and that would be who. So I'm not going to tell you what who does right away. I'm going to run it, and I'm going to let you see what you think it might do. So when I run it here, it says the interactive namespace is empty. But let's say that we go ahead and declare a variable here. So I equals 10, and then we run I equals 10. So now it's accepted it. And then we do %who again. And now it's identified that I is in the namespace. So who takes a list of all existing variables in the namespace, specifically that you have declared, and lists them out for you so that you can see them. This can be really important when, again, you're running a much larger program and your Jupyterlab notebook is, 100 lines long, and you don't necessarily know who all are the existing players in the notebook. But let's go ahead and try something interesting, because we can remove lines, right? So let's say we remove I equals 10. We take out this %who, and we're going to run our magic command again. since that declared variable is gone, do you think that it will continue to show up, or do you think that it will disappear? When I run it, you can see that I still shows up because it's still a part of the namespace, even though it's not listed. It's part of what exists in this project's kernel for now. However, if I run it again, if I restart the kernel, it says all variables will be lost. So when we restart it, if I were to run who again, you can see it's back to being empty. So that way you can be aware of what variables currently exist in your namespace, even if you've potentially deleted them or you think you've removed them by removing a cell, you haven't really removed them from the namespace. They still exist somewhere in there, and you'll need to restart your kernel in order to clear out that interactive namespace. Just to recap, magic commands are special commands that you can use in Jupyter Notebook specifically, and they extend the functionality of your existing Python kernel. They are a feature of IPython, which is the interactive Python shell that you're using, similar to when you run idle in interactive mode. They also come in two types. So there is that single percentage line where the line or command that you're using applies to a single line of code and therefore is prefixed with a single percentage sign. And then cell magic commands are applied to an entire cell of code, so multiple lines, and they're prefixed with a double percentage sign. Like I said, we used who, we used time. There are lots more magic commands that you can use, and if you want to find out more about them, I'm going to tell you what I always say, read the docs. So here we can get a quick guide by running quick-ref. So if we run quick-ref, here's a bunch of different magic commands, as you can see, that you can go through. They tell you exactly what they do. They give you a quick way to use them and everything you need to know about these commands. It can be a little bit tough to get the hang of at first, but if you have any questions about it, once again, you can reference that documentation on the lovely Jupyterlab's website. Now that we've gotten a little bit more comfortable with Jupyterlab, let's go ahead and talk about one of the primary libraries that we'll be using in Jupyterlab, and that is Pandas. Pandas is a Python library that's built for working with data sets. It's kind of your go-to toolkit for loading data, exploring it, and reshaping it into something that you can actually use. It's essential for cleaning data with a larger table if you're referencing it in Python, and then going back into it, analyzing it, and exploring it. This way, you spend less time messing with the files, and you can learn from them instead. This is important because you can have a massive data set and all the data points in the world, and it really doesn't matter unless you have someone that can interpret and use that data to draw conclusions about what it is that you need to change or implement in order to further your goal. So you really need Pandas to clean that messy data and then process it so that you can go on to start making conclusions and ideas from the data that you see. Oftentimes, I have found that when I'm doing data analysis, I start out with a question, and then as I research that question, other questions come up that seem relevant, and I start considering how I can better work with the data that I've got and draw more important or relevant conclusions from the trends that I'm finding. Some of the more important things that Pandas can actually do are check correlations between columns when you're looking at two different columns and see if there's a relationship, compute averages, things like max or minimum values are also important. It can drop bad values, so if something is empty or it seems completely off, you can use Pandas to tidy your data set and then model the visualization. And this data cleaning is built in and pretty straightforward. The name itself is interesting. It comes from both a nod to panel data and Python data analysis. It was created by Wes McKinney in 2008, and it's still a core part of the Python data stack. And if that doesn't tell you just how important and foundational this library is, I don't know what will. Now that we've got our basic concept of pandas down, let's go ahead and start using it. So first we have to install it before we use it, and that's going to be the same process as we did with Jupyterlab. It's going to be the old pip install pandas in your command line. And if you have a different package installer, you can use that as well. But the important thing is that you install pandas in your namespace, and then we are ready to go ahead and use it. So since this is our data analysis project, let's go ahead and move small data set, which we'll be using, over there so that we can look at them at the same time. And then I'm going to go ahead and clear this out. And remember, pandas is a library, so we need to import pandas. And then usually people reference pandas as a shorter variable name. Commonly, I see PD. So we're going to say import pandas as PD. And then if we run it, it should be like, yeah, okay. So it figured it out. And now let's go ahead and make our first data set. So I know we have this big, it's called small data set, but it's pretty large. So let's go ahead and make a smaller one and see how pandas takes it. So in this cell here, I'm going to create a baby data set. So let's see, we have a dictionary here. And in our dictionary, we're going to have people, or users, you could say, since we're sticking with our theme here. And then we'll come up with some names. And notice what we've got in here is we've got a dictionary, and then we've got a key. And inside the key, we've got a list. So there's 3 people. Go ahead and close that list. And then our second, oh, sorry. Didn't like the way I structured it, but that's okay. We can go ahead and keep adding on to this. We are going to, for our second entry, enter another key here. Let's do years. So the number of years that the person has been with the company. And just for simplicity's sake, let's go ahead and make these strings to start out with. But that's another thing that pandas can do, is if you have just a single number like this, you can convert it into an integer. So we've got, say this person's been here a long time, they've been here 12 years. And we close that, and then we close our dictionary. And now here's the real magic. We're going to go ahead and convert this into a data frame. And we're using an object here and passing in our data. And then we're going to tell it to print our frame so we can see what we got. Oh, I didn't like it. Oh, my bad. It's because I changed the name to make it shorter so that it would be easier for us to use. Let's go ahead and run that. There we go. Now it's working properly. And you can see here are the entries. So we've got Jen, who's been here for 1 year, and there she shows up. And our labeling is here too, which is nice. I mean, this is a really nice way to visualize data if you are just working in Python normally, because you can have Python reference this as a matrix, but it's not going to show up nicely formatted like this. So what the data frame really does is it formats it for you, and it says, okay, these people are associated with these years. Jen has 1 year, Alex has 2 years, and it associates them together so that you can then draw conclusions about which people have which attributes attached to them, or as we're going to see in just a minute here, which computers have what attributes assigned to them, and it just keeps everything nice and neat for you. We've had a chance to look at a smaller data frame and data set, but generally speaking, when you do data analysis, you are pulling from a data set that's larger than 3 people, and generally speaking, that means you're going to be pulling it from a file. So let's go ahead and do our first data analysis from a file with Pandas and create our first data frame from a file as well. To start, let's go ahead and create our data frame with this. We're referencing Pandas with the PD and then calling a function that it has, which is read CSV. Now notice, yes, we are reading a TXT, but importantly, the TXT is in the structure of a CSV. So we can say, oh, just go ahead and treat this like a CSV. It's just another form of text file, but it has comma separated values. And that's what you really need. So we've gone ahead and read it. We're going to start, well, we've told it to read it, and now we're going to tell it what file to read. And then we're going to say parse dates, which means there's a column in there named date. When you see that, know that it's trying to reference a date. And go ahead and try to figure out what that date looks like, so that then we can sort it by date if we need to. Let's go ahead and look at another concept, which is the categorical concept. So we have 3 categories of device here, right? 3 different health levels. We have warning, healthy, and critical. And critical is of greater concern than warning, and warning is of greater concern than healthy. And most importantly, there are only 3 things that this column can be. You can have healthy, you can have critical, or you can have warning. And as long as we're sure that we don't want any other values to be available for that column, we can start filtering and organizing our data set. So let's go ahead and give it an order first. I'm going to tell it, here's my order. We'll list healthy first because it's of the least importance. Usually you well, not usually, it's up to you. But in my mind, normally I list from least to greatest when referencing a list. So we're going to say healthy, then we're going to say warning, and then critical. Now that we've done that, we can say, okay, data frame, health status, which we have up here, this guy. Health status is a categorical. Okay, so this might look like some word salad. Oh, no, thank you. This might look like some word salad, but it has multiple different items here. So if you look, we have, okay, I want to restart that, sorry. We have multiple categories here. We're looking at the health status, and then we're telling it for the categories, go ahead and look at our status order here. So when we look at organizing our data set, what does that mean? Well, we have a status here. We have warning, healthy, critical. One important thing about these, there could only be 3 separate values. Now we've seen that in our data. If you don't already know that, it would be best to ask whoever collected the data. And if you intentionally collected the data yourself, then you should know if there are only 3 categories. But Another thing to consider is that there are different levels of importance. So for me personally, I'm going to want to look at a critical device before I look at a device with a warning, and then healthy devices can be evaluated last because they're not having issues, so they don't need to be looked at right away. So we're going to go ahead and order these by status. Status being the current health of the device. So here we're going to make a list, and this list is just to tell Pandas, hey, here are these options. This is my existing values that could potentially be sorting options. And these are all of the values that I want to use. If you see anything else is not good, throw it out. So now we're going to say Dataframe, health status, which there's a column for that right here. So we're pulling it from there, but we're turning it into a categorical. Oop. So we're telling it, hey, it can only be these 3 values, and there's an order to them. In this case, I mean, you don't have to keep the names consistent, like the variable names, because notice I have health status and health status here, and that can seem a little bit confusing, maybe, but I personally like to keep the names consistent between, because it doesn't really change how you're writing about it as long as you understand the difference between what your data frame is and what you're pulling from. So here, this is telling the data frame that we're going to have something named health status. And then here, this is going to be pulling from our existing data set in smalldataset.txt. And then this is saying, hey, there are in fact categories. To find the categories, pull them from status order. So if you see anything other than these categories, don't allow it. And then finally, we're going to say ordered equals true. Ordered equals true means, hey, these are in an order for a reason. We've listed healthy first and then warning and then critical. And the reason for that is that critical carries more weight than healthy, right? So we could put all of these values in a certain order and know that they're in that order for a reason. We'll go over a little bit more data cleaning later, but in the meantime, I want to go ahead and run this so that we can have a little look. So let's take a peek here and say display. So it's kind of like print, show me the head of the data frame, the first 5 rows of the data frame. And when I hit run, we can see here's all my nicely sorted data. Now, notice we haven't told it, it can be kind of confusing because we haven't told it to sort by status order yet. We would need to make a specific call and say, hey, go ahead and pull all of the devices that have greater weight than healthy, right? So if it's warning or critical, go ahead and pull that data. But right now, we've just asked it to pull the head. So here's that first 5. We don't have, at least in the first 5, anything other than warning, healthy, or critical, which are the categories that we said we'd be comfortable with. And you can see it's just a bit better organized than referencing this. But while the formatting looks nice, the truly most important part of this technology is that sorting it into a table like this allows Pandas to then draw conclusions from this data in a way that it can compute and reference it quickly. We've got our data into the data frame, and that means that it's time to do a little data triage. Let's investigate and make sure that all of our data is good and just sanity check everything that we loaded in. Personally, I want to know how big our data set is, what types of data we imported, if we have any missing values, and if any columns are being a little extra dramatic with some wild min-max values. We can also look at the category distributions and see if anything's lopsided. So hopefully we're seeing a lot of healthy devices and it's lopsided in a positive direction. But if we're seeing a lot of warning or critical devices, then that means we need to check for whether or not there is truly a critical problem to do with our larger technical system, or if the threshold to flag a device as warning or critical needs to be raised so that we're not artificially flagging devices as unhealthy when in reality they are healthy and do not need our attention. So to start, let's go ahead and look at a compact summary of our data. We're going to go ahead and say dataframe.info. So give me some info on my existing data frame. And go ahead and give me all the bells and whistles here. Let's see what we get. Boop. All right. And now this is useful. You can see we have 300 non-null values all the way down. And we've got a DateTime object, which is perfect. That's exactly what we told it to read that first date as. We've got a couple objects in there. It's in, I don't know exactly what those are, but they're some type of object. And then we've got a bunch of numbers that are float 64 because they are big numbers, or numbers with a decimal point in this case. And then we've got that category that we set, right? So we said, go ahead and look at your frame and force health status to be a category. It can only be one of three things. It has to fit within this category. And then finally, we have a Boolean value for a ticket opened, which is good. That means it found that everything was true or false. Nothing fell outside of the expected ranges. We are good to go on that. That deep flag is going to give you a more accurate footprint of all of the items, but if memory looks too high, you can convert the free text to category if you need to, just to kind of lower it a little bit. So even though we already have this information, let's say that we want to do something a little bit less in depth and we just want to look at the data types. In Pandas, they don't call it data types, they call it dtypes. So when we run this, it's going to show us all of our data types, just like our general summary did. I think the general summary is probably going to be your best bet just for a quick look at the data. And then also I use it to make sure that nothing is missing a value. So if everybody else had 300 and then ticket opened had 299, I would be looking at my data and saying, where is this value missing? And then can I either add that value in or fully delete the record before rerunning my data frame and asking it to include the now cleaned up data again. Let's say that something was missing, but it didn't tell us which one it was. We could go ahead and run this command. Which says, find anything that has a value that looks out of place, it's not behaving how we want it to, and then go ahead and count them per column. So if it seems like date is missing a value, that first comma is missing, go ahead and count one. Or if OS is missing one, go ahead and count it there and then list it for us in that itemized list of existing types. Let's go ahead and have it describe now. So it goes ahead and gives you a summary stat for numeric columns. So in this case, we're going to tell it numeric only because in recent updates, it's gotten a little bit unstable in how it determines things that aren't numeric, which is reasonable. I mean, it's hard to define how exactly to look at data that isn't numerical in a data analysis program. But if we run this, oh, I didn't like it. Let's see. Oh, I didn't like numeric only. Okay, that's okay. Now I want an overview of all of my numerical options here. So in this case, we've got a few numerical values. We've got, say, Adobe runtime, which if you've ever worked with Adobe, you know that Adobe crashes and is generally just impossible to work with. We've got CPU usage percent, which is also good. I'm guessing that that's an average of usage percent over time. Same with memory usage percent. It's just an average, or it could be a snapshot in that moment. Either way, it's useful to us because it gives us a little peek into what that device is doing. So let's just get an average of what all of our devices are doing as far as we know. So here, I'm going to tell it, you get a little wonky when you don't just have numerical values and you're assessing everything. So go ahead and take numerical values and then describe them for me. All right, and then check this out. So we've got the count, the number of entries that we have. We've got mean, which means you add them all up and you divide by the number that you have. And then we have STD, which means standard deviation. So that is the size of the data set. It's looking at where the clusters of the data set are, and then where it gets very high on one end and very low on the other, and assessing how good that standard deviation is. Something interesting about that is when they are quite high, you might be a little worried, but in this case, they look good. And then we see the minimum value. So this is the lowest value of all 300 entries. And then the 25th percentile. So that means I shouldn't say percentile. It's the first 25%. So the first quarter of values fall at or below this number. And then 50%, half of them, fall at or below this number. And then 75% fall at or below this number. And then finally we have the max, which obviously is the highest number that is found in that data set. I'm also just going to go ahead and close this guy. But yeah, this is useful to us because it can help us evaluate discrepancies. We can look and see if there are any major outliers, right? It looks like 15 maybe isn't too far away for uptime hours from 25%, so it's probably okay. If you look at this, Adobe runtime it's a good thing that it's a lot shorter here, so that isn't necessarily something to worry about. But if we look at the max, we're probably going to say, who in the world has had Adobe running for 334 minutes? We probably need to go check that out. And then in this case, 95% CPU usage, probably need to check on that device as well. So all of these things are insights and components of a larger picture that we are gaining from this short little description of all of the numerical values that we have from our data. Earlier, we were talking about calculating the distribution of healthy, warning, or critical devices. So let's go ahead and do that now. Remember that earlier we said that we wanted health status to be a category, right? So there were only 3 available items that health status could be. And now we're going to count those. When we run this, you can see there are 236 healthy devices, 42 have a warning, and 22 are critical. So what does that tell us? That tells us that our distribution looks about how we want it to. I would say we definitely want most of our devices to be healthy. Some of them are critical because they're having errors right now, but it doesn't seem like our measurement of when a device should be considered a critical issue or having a warning are really outside of what we would expect. This distribution looks typical, and we know that it looks appropriate for what we were expecting. Granted, if you only have 100 devices and 22 of them are critical, then you're probably going to want to go ahead and look at what might be going on with those devices and or editing the threshold for considering a device critical. But in a case with 300 devices, I'm very happy with that. I think that 22 in a critical state is an acceptable number and our data is good. Let's go ahead and look at our timestamps now. So let's say we want to know how old and how new our data might be. Like, for example, perhaps there's something far away or pretty recent, and we want to check out what's recent or newer. So really quick, let's go ahead and run that. So another data validation method that we have is a quick min and max comparison for our various columns. Let's say that I want to take a look at our CPU usage percent, memory usage percent, and just see what the minimum and maximum of several different columns are, which you can see we're pulling these from the names of our columns here. But I can request the min and max of each column. So let's go ahead and do that. This is useful if you're wanting to, say, check for outliers, like if CPU usage was at 100%, then that might be worrisome, or greater than 100%, especially, that would be an outlier, right? Or if something was at 0 or less than 0, those numbers would be impossible. So we want to make sure we're keeping track of values and keeping in mind what would be a reasonable value for it to have. Just going to do these three here, just for a quick example. And they're being pulled, again, from our column names here. You can see them up at the top of smalldataset.txt. And when we run this, there you go. So the minimum for CPU usage percent is 1.2, which is extremely low, but still within the realm of possibility. And 95.6, which is quite high, but again, I've seen 95 or 96% CPU usage, so this is okay. The min for memory usage is 1.9, and the max is 100. While 100 is not good, it is possible. And then for the last one, the disk-free gigabytes, we've got a minimum of 10 and a maximum of 455. Now, 455 is quite high, in my opinion, for an amount of free space, but it's not impossible. We'd probably want to investigate, what size memory they had to start with, and if they have any auxiliary memory that's being used first, right? So when you see something that looks like it could be an outlier, that's when you go back and you ask more questions from where you received the data. Instead of looking at the data itself, you might ask a question about, well, why does that number look that way? Now that we've gotten to take a look at data frames, what they are, and how to get a brief peek into your data, I want to talk about how we can slice and dice our tables. So a data frame is pretty much just a table. Columns are the features or variables, so things that we've told it. For example, our CPU usage percent here, or our host name over here, but they're things that we've already established to have a value that we've named, and the Pandas data frame pulls it from the first row in our CSV, or in this case, a TXT file that is CSV shaped. Rows have an index, which by default usually starts at 0 and counts up to 1 below the total count of items, but you can also set it to be something else, like the date, if that makes more sense to you or helps you process it. Just like how we use a spreadsheet, sometimes with a data frame, you only want to look at one column, maybe a couple columns, or specific rows, or even just one cell. So Pandas gives you the ability to do all of that pretty quickly. There are two main ways that we think of that you can grab data frame information. So if you're pulling it by label, that means you're pulling it using the name. So for us, again, date, host name, OS, stuff like that. And then if you're pulling it by position, you'll be using numbers. So row 0 through 5 or column 0 through 3. You can reference those numerical values in either way, and you don't always have to use the name that you've given it. But if you want to reference it with labels and conditions, you're going to use .loc or location. And then for integer positions, you'll use .iloc, right? So integer location. So once we understand that, we can go ahead and take a look at some quick examples. That way we can better nail it down. To start, we can skip what we were using, like even skip the .loc or iloc because we've seen these before. So we can print the head of the data frame, right? We've seen this, but I'll go ahead and do it again anyway. Whoop. Just so that we remember, like, oh yeah, I've done this before. And we're just going to print the first 5 rows. So let's print the head here. Close that guy off. And there you go. There's our first 5 rows, or yeah, sorry, rows of just CPU usage %. So this should be these here. And if we look, 49.2 is right here. And then we've got 59.3. So as expected, it pulled it straight from the data and it said, here you go. Here is exactly what you wanted. But let's say that we want to pull multiple labels at the same time. We can do that too. Usually you're probably going to be pulling multiple components like this because one piece of data on any given entry isn't necessarily going to be enough for you to have a good picture of what's going on. Oh, I didn't like it. Oh. Yeah, that makes sense. Oh, whoopsie. That's what it's upset about. Sorry, took a second, but here we are. We've got 3 separate values. We've got the host name, the date, and the CPU usage %. So now that we've taken a look at those and we're kind of getting comfortable in our usage again, let's go ahead and try out that integer location. So print. So we're printing our integer location here at position 0, which means we should be printing out the first row. Let's do a little practice here with the .loc and how to implement that in your sort of searches and slicing and dicing. So to start with, let's look at a specific status. So in this case, we're going to be checking critical devices because to me, critical devices are one of the biggest concerns and I want to know why they're critical. So let's go ahead and make a label for that, which is what this is right here. This is saying, go ahead and take a look at health status. Specifically, if it's been labeled critical. And let's go ahead and print what happens when we pull those using that .loc there. And then just the head, right? So just the first 5 rows, which we usually want to pull more than just the first 5 rows, but this is just to give you a little demo here. And then when I pull that up, you can see here are the first 5 devices. This is useful if you're trying to get a quick glimpse at something, or if you just want to look at specific data from a label. So I don't necessarily want to look at all my devices at once, but I just want to look at the critical ones really quickly. But let's say that I had a secondary question. Let's say that I thought, the health status is interesting, but I also want to know the CPU usage percent. Maybe the CPU usage percent is relevant to our current device health. So if I look into that, let's go ahead and test that. Actually, I don't want to print. I want to start by making a label for the CPU here. So this is going to be similar, except now we're going to assign a value that we consider high, right? Because I don't want to pull all the same devices. I want to pull specifically devices that we consider to have a high usage percent. And for me, I consider that to be 80 or above, just because I feel like it starts getting kind of risky above 80. So let's go ahead and do that. And this is just establishing that there is a label, and then we can go ahead and pull now. We're going to use ampersand to tack the two conditions together, and then we're going to say, and here's all the information we want. We want the date, host name, and as usual, we're going to pull the head because this is just for demo. Boop. And when we run that, what do we get? Boom. So we've specifically only got 2 devices that have a high usage percent and they're in critical status. So if we wanted to start narrowing down which devices really needed attention quickly, we could go and check out these host names and see if there's any applications that are crashing or ask the user about them. But immediately we know which devices are most important to be checking in on and why we might be having issues with those devices. This is where you can see having data really starts to narrow down the questions and the problem identification skills that you have, because the more data that you have and the different forms of data that you have can guide you towards a potential solution to a problem. Now that we better understand what a data frame is and some quick ways to sanity check your data and make sure that your data is good, I want to talk about rows and columns and the ways that we slice and dice our data. A data frame is pretty much a table, and the columns are features or variables, so things that we've already named personally, like in our file. If you notice up at the top, we have host name, OS, things like that. So those would be the column reference items pretty much. And then rows have an index. So by default, that's usually starting at 0 and then counting up to 1 below the total count. But you can also set it to something meaningful, such as the date or whatever makes the most sense based on the data that you're using, should you so choose. Since the columns are those features or variables, you can think of the rows as the observations that you've made. In this case, with our data, it's pretty much a daily record for each specific workstation, and it's useful to us because then we can identify where there might be issues with our devices. So there are 2 main ways that you can grab data from your data frame. The first is by label. So when you use the name, like host name or date, those quotation marks that we saw, right? Like with date here when we're pulling the min and the max. And the other way is by position, meaning you can use numbers such as row 0 through 5 or column 0 through 3. If you don't use that data frame format that I've shown you before, there's 2 separate ways that you can handle it, and those are .loc, which is the location for labels and conditions, and then the .iloc, and that's for integer positions. Once you fully understand how to use these, you can quickly and easily jump through your data and pull exactly what you need. Since we've already seen that implementation without .loc and .iloc, let's go ahead and play with those two new toys that we've got just a little bit. So to start, I'm going to go ahead and display the first row. So let's say print, or not print, in this case we want to display. So this is display using that reference ID at position 0. And when we run it, there's a nice quick view of that first row that we've got, displaying all the components. And if you look, yep, that's the same as the first row in our document. And now if we want to print the first 5 rows, let's do that, or display it. Now you're going to notice I don't put a value in the first part because that implies just take it from the beginning. And then I go up to 5, which sounds right. And if you look at the numbering, oh, it goes up to 4. Why does it go up to 4? Because it starts at 0. Just like any programming language will pretty much always start at 0. So here's all our stats for those first 5 devices. And it's a nice quick way to display just those 5. You also could do something similar. I'm just going to copy paste this because it's a really similar item. But if we didn't want to start with this, we could do like 250 and then whoop, go up to 255 and run that, and then 250 to 254. There it is. You can just pull a very specific group of devices, and especially if your data is ordered, that's going to help you quickly find what you need. So now that we've had a quick look at that, let's try using that .loc. This next component is 2 concepts rolled into one. It's being able to sort by dates, which I feel is important if you're using chronological order for a set of data that you have, and also a mask. So a mask in Pandas is the concept that you can have a Boolean value to establish whether or not you want to see something. If we continue to follow the logic that we had with our device being critical, we could say if the device is critical, then the condition is true, otherwise it's false, and I only want to see data where the condition is true. So that's a very high-level explanation, but let's go ahead and write a little bit of code for this. So to start out with, we're going to set our mask. So here's that item that we're looking at, and then we're going to just look at one host name. Well, if you look at these, the first 30 entries or 31 entries here, no, 30 entries because we're missing this one. So the first 30 entries are all device WS001. So we just want to look at that device. And we also want to look only at that device on certain days. So now we're asking, is time relevant to the health of our device? So here's our date. And remember, we already told Pandas that this was a date, or rather that this format had a date in it when we ran one of our earlier lines here. It was a while ago. Here it is. Yeah. When we told it to parse the dates, we established that that was in fact a date. So now we can just say, since you know that these are chronological, go ahead and look at any date between between October 10th and October 20th. Except I want to do this here. Not 100, that would not be a date. There we go. So we can use that to establish our mask. And then when we go ahead and use our mask, we're going to say, I'm going to ask it to print again so that we can see that example. We're going to use LOC. Now here's our mask, and that's in our first set of parameters for that LOC, if you will, or arguments. And then we're going to ask for date, and then the memory usage percentage, because we already know what device it is. We already know what potential stuff it could have, like for the host name or the date. So we really just want to look at what day it was and what the relative memory usage was to see if those two things are linked. So let me finish this up here. Close that. And then let's just get the head. Now that we have the mask, let's go ahead and take a little peek at that data that it created, or the data set rather, the subset of the data, if you will. So let's get that LOC again, and here's our mask that we talked about earlier. And now we're going to enter the parameters, or the data that we want to be included. So here's all the essential things that we want to see. And I'm just pulling these from our names up at the top of our small dataset.txt file. I know it's getting a little long-winded, but we're going to go ahead and close this. And that closes out the arguments that we had in there, but now we need to use the head function and then close our ask. And if I run this, there you go. And it lists out very nicely for you: date, host name, health status, usage percent, and memory usage percent. And if we look at the data that we have established here, it seems like it goes back and forth between critical and healthy. But if you look, it looks like the CPU usage percent and the memory usage percent are very high on the first time that it's critical on October 10th. But on the 12th, they are much lower. So that suggests that maybe at the time the health status was considered critical for different reasons on either day. Also, if you look, the memory percentage on the 11th is very similar to that of the 10th, which tells us that maybe just the memory usage being high alone is also not enough of a factor for it to be considered a critical machine. So we're starting to narrow down what the possible issues might be and what the issues aren't, right? We see on the 12th that they're probably not related to what we pulled. So we might want to pull something else to figure out what was going on the 12th. I know this video is getting a little bit long, so I was debating running these last few sections, but let's just power through them and then we can wrap up here. So what I want to talk about next really quickly is creating another mask, but with additional parameters, and the concept that you can create a sorted category like we talked about earlier, and then use that later to sort. So let's go ahead and reset our mask. And when I say that, again, it's just a variable that we've named mask, but it's conceptually a true or false Boolean that we are messing with. And now we're going to say is in, and then we're going to create a little list here of device names, although there's only going to be two, so some list, but big enough that we need it. There are two device names. We're going to close that. And then, oh, that is not right. Okay, there we go. Then we're going to have another conditional. So we're going to put the ampersand in there. And the other conditional involves that health status that we were talking about. So here's our health status. and greater than or equal to warning. So if it's a warning or a critical, it should show up, which is kind of nice. It's kind of nice that you can do that. So we're telling it we reset the mask, and then we're going to print that and see what we get. Or once again, the head of it. Oh, not hate. Okay. Date. And then memory usage percent. And if we run that, what do we get? Boom. Okay. So if we look at these, here's our CPU usage percent and our memory usage percent. Really, we've asked it for, you can see the data that is available, and it can be helpful to do something like this if you need a quick look at something that has a rating of warning or greater. But all of these are device WS003. So if we go down to that and then look at some of the devices here, the 1006 entry does have a rating of warning. So that tells us that it's correct in what it assessed and what it added to it. Things like this can help you really narrow down your data and establish what you want from it. I know that this was a pretty heavy-duty first video and introduction into data analysis, but just as a quick recap, today we went over a very high-level overview of what data analysis is. We took a look at the Pandas Dataframe and Pandas as a tool specifically. We took a look at Jupyterlab and how to run Jupyterlab, as well as how to have multiple windows open in Jupyterlab and a couple ways that you can best use it, like magic commands and other small tools. And we also took a brief intro into our masks and ways that we can evaluate data sets by giving specific parameters to pandas. So hopefully this was helpful, and welcome to the world of data analysis in Python. In the previous video, we talked about pandas, data analysis, and just a brief introduction into what we'll be working with. So this time, I'd like us to talk about how to actually do data analysis. And again, we're going to continue to use our semi-real data set, and we'll use this data by exploring it, transforming it, and ultimately, and probably in the most exciting part of it, build visualizations with Pandas and Seaborn. There's a few commands that we're going to need for this. We already have one of them in here, but I'm going to go ahead and create a new project here, or not project, but just a new Python file so that we can start over fresh. So let's go ahead and open this, and we can rename it to data analysis 2. And let's import. First, we're importing what we already know, pandas, because we do use pandas a lot and we will continue to use it. Now let's import something else. Let's import matplotlib, which is really good for data visualizations. So specifically, we're going to ask for pyplot. There's our abbreviation there, so we don't have to type pyplot the whole time whenever we want a new pyplot. And then finally, we're going to import Seaborn. I'll go into Seaborn in a little bit more detail as time goes on. But for now, let's just leave it at that. So let's start with how you would go about examining a piece of data. To do this, we would always start by asking, what do we want this data set to look like? What's the shape of the data? We want columns, rows, row counts, data types, and a quick statistical snapshot, which we took a look at last time, right? We saw that in our read here, or looking at the head, or getting a deep view. So there's many different ways that we can reformat our data to kind of make sense of what we're looking at. And we've got this describe here that's describing in depth what the shape of the data looks like, kind of, and where the most data points are. With that review in mind, let's go ahead and get started on some data visualization. Chances are, in the past, you've seen some form of data visualization. A lot of times we see it as a line plot or a bar chart or a pie chart, but it's basically just a synopsis of the data that you already have. And it can be really helpful if you need to communicate something about your data in a short period of time. So something where you might have seen this recently would be a weather application where they use the highs in a bar or line plot sort of visualization, but it's useful for you when you need to communicate something to a coworker or a manager and basically just quickly show them a conclusion that you've drawn about the data. In order to do this, let's go ahead and start with a line plot because I think that's one of the simpler visualizations that we have. But I did notice that I am missing something here. And I said it, and then I didn't type it. There we go. And now I'm going to save this. Is it going to let me? Okay, well, I would like to rename this. I want my data frame back because we spent a decent chunk of time looking at this data set and explaining how it worked in the last video. So I'm going to put this here. I'm going to let you have a look real quick in case you need to get caught up. But basically, it's going to help us read in all of our data. Now I'm going to run this so that it's in our notebook's current kernel. And now we can start working with this. Let's start by sorting it. So we're sorting by index here. Whoops. And now let's create a variable for specifically the hostname ws-001, which I'm going to name ws1 for simplicity, and also because certain Python applications tend to freak out a little bit if you use special characters. I'm not sure if that's part of the compiler for Python, but anyway, I digress. So here we're saying, look at host names, and specifically, I want you to look at the host name that is equal to ws-001. Here we go. So now we're going to take a look specifically at WS1's uptime hours. So this is saying, just for this device, go ahead and take a peek. So plot this for me. We're saying, what version of a plot do we want? And let's make a title that makes sense. It's the same as it's the same as when you name a variable. So we want the variable name to make sense for what we're doing. So here we're going to say, well, this is common etiquette in science. I'm going to say x-axis versus y-axis. So uptime over time here. And then the device that we're looking at. And we're going to plot it. So here's our X label, which is the date, and our Y label. You know, done all this math in my life and still I have to think about which one's the x-axis and which one's the y-axis, which sounds so silly, but sometimes you just got to think about it for a minute, you know? No shame. I will not have any shame in my math. And there we go. That's pretty cool. So you can see it tells us the uptime, the number of hours we have over here on the x-axis. So you can see, as labeled in our little plot code up at the top, we've got hours on our y-axis and date on our x-axis. So that's saying what date, what did this happen on, which date is a very common X label to have, and then how many hours of uptime were there on that day. So we can tell at some point they had very little time on the computer, but for the most part, the number of hours running is high. And even here, it's a little bit misleading the way that this graph is set up, because you can see the lowest we get to is 18 hours, which is a high uptime, right? 24 hours would mean it was running the entire day. So this computer has been running a lot. But let's say we just change this. What happens if I decide that I want a bar here and I just put bar? Now Python does that, but if you take a little look there, that doesn't make any sense for the data that we're doing. I mean, it's fine, but which one do you think is easier to read for the data? Like, what are we trying to communicate here? First of all, we're trying to communicate the amount of uptime. And then second of all, we're trying to communicate the dates. So the interval of dates that we have here would be a little bit overwhelming with the bar chart. So my point is just kind of different data has different graphs that are sort of meant to be used to model that data, and it's up to you to decide what the right one is for you, so to speak. Anyway, I'm going to put this back to line because that's what I want. And now we're going to take a look at a different set of data and try a histogram. You've probably seen a histogram, even if you don't know the name of a histogram. So let's just type it out and let you have a look for yourself. For this one, I want to look at CPU usage percent. And then bins. What does that mean? You're going to see. Unless you already know what a histogram is, in which case you probably have a guess. Again, we need a title that makes sense for the situation. And let's show it off so we can see it right away. So when I run this, you can see that we've got our frequency here. And then at the bottom, we have got intervals of 20. And it's showing the frequency, so the number of times that the usage is at what percentage, right? So the most CPU usage was probably at about 50%, and it happened almost 40 times. So that's useful for us if we need to see the distribution of data points for a specific device, right? Like if I wanted to see what the average usage distribution looked like over a number of days, this would be helpful for me. Or if I wanted to look at a different data set and I was looking at employees, and when I say the CPU usage that is highest, I don't literally mean the CPU usage percentage. I should correct that, because the highest usage that we see is at about 90%. But what I'm really saying is the highest frequency that we see of CPU usage percent is going to be at 50%. So part of, or I guess another part of the visualization skill is just understanding what it is that you're looking at when you're looking at this data set, A, and more importantly, B, what that data is communicating to you. What does this mean for your computer? So this means to me that this device is usually at a pretty healthy level of CPU usage. I've seen CPUs jump to 70% over something silly. You have too many tabs open, you have too many programs open. That happens, even to 90%. And maybe if it were hanging out at the 25 to 30% range, I would be worried about about that. Like the frequency, if the frequency jumped, I would be worried about that. But given the low amount, I doubt that CPU usage is part of the issue. Looking a lot more like uptime might be the issue here, just from the graphs that we're running. With that in mind, let's go ahead and explore another plot here. Let's take a look at a box plot. I know we're back to school here with all of our plots. but here we're going to say what we want for the columns. Wait. And this is just, instead of the frequency, we're going to look at the health status. And then this one's even more obvious than the previous ones because it literally says by. So you can say CPU usage by health status. It's already written for you. And let's have a look at what this plot looks like. There you go. Okay, so these are a little bit harder to read, but they have a lot of useful information in them. So what can we see here? We can see outliers, maximum, the upper quartile, the median, the lower quartile, the minimum, and then lower outliers. So to start with, let's look at our upper circle here. Our upper circle is our outliers for the upper quartile. So they have to be more than 1.5 times the upper quartile. And then we have the maximum. So this would be our maximum. So if you look with warning, the CPU usage, that outlier is way high. It's at like 90% compared to the maximum that we see within the, like excluding the outliers. The next one that we see is at 72 or 73. And then once we get past that max, we can look at the upper quartile. So this is the top 75%. So from here up to here is 25% of the data. And this line here is our median. So the median is 50% of the data is greater than this value. This is the middle of our data set. So the middle of our data set is at about 50, which makes sense. And then our lower quartile is here, which if you notice, these are not equally spaced because they don't have to be. It's just about how your data is distributed. So the bottom one is the lower quartile. That means that 25% of the data is less than that value. And then we see the minimum, which is the lowest value excluding the outliers. And we don't actually have any lower outliers here, but we see a couple in the healthy area. Now, in this case, we have to be critical about what exactly the data is that we're reading and interpret it. So for a healthy computer, it makes a lot of sense that we would have a very low CPU usage for several of the devices because it looks like we have a couple devices maybe that are overlapping each other in the healthy space. So those devices don't really use a lot of CPU usage consistently, or they're experiencing lower amounts of usage than the warning status ones at their base or even the critical ones. And you can see that our data does make sense. It kind of trends upward as the health of the device decreases. Interestingly enough, we see a dip in the upper usage here, but we see a very high outlier, which makes me wonder what that means for our CPU usage overall with a warning on a device. But with critical, it definitely aligns with what we were expecting, which is that we have a very high upper limit, although I will say that our upper quartile is lower on critical. So what that tells me is that it's possible that the health status is not directly influenced by CPU usage. It does seem to be correlated. There's some form of relation, but I'm not sure that this is a causation situation. I'm not sure that our CPU usage is causing negative health status. So now that we've had a chance to take a look at our data visualization basics with Pandas, I would like to delve a little bit deeper into those, but also explore a new technology, and that is Seaborn. Now, don't get me wrong, there is absolutely nothing wrong with Pandas. It makes great visuals and is wonderful if you need to use it with your existing data and just create a quick visual. However, Seaborn does offer more variance and can tell a better data visualization story thanks to its arguments like hue or size or style, and it also is helpful when you need something that's multicolored and can help you visualize your data better. So it's a little harder for you to see that or understand that without me showing you an example. And I'd like to give you an example of both a new type of plot in Pandas and that same plot in Seaborn. So let's start with the Pandas version. Okay, so we have this set of arguments, and we're going to ask it to show the plot. When we run this, here we go. Now there is nothing wrong with this, and it looks visually like it makes sense. We can see here we've got memory usage percent and CPU usage percent, and we're just looking at a plot of the two of them. But let's try a same scatter plot in Seaborn. In case you're wondering where this SNS is coming from, it's coming from our initial import statement here, where we say import Seaborn as, which is an alias SNS, and that's to make it shorter and easier to work with. And then immediately we're going to say, take the data from Pandas. Let's not bother trying to re-input it using Seaborn or reinvent the wheel. Let's just use our Pandas data from the jump. Oh, I don't like how that's spaced. Hold on. So I know this looks a little different, and we're going to see why in just a minute here. So when we run this, you can see that it's showing us the same stats as it was before, and the data looks just the same. We can see here there's one much lower stat, and there it is right at 40, same spot for both of them because they're plotting the same data. But also we have health statuses and their colors. So we can see based on this data that there's a warning device that has 100% memory usage percent, but very low CPU usage percent. And we know that that same device exists right here, but we don't know the health status of that device unless we were to be here. So you can see how Seaborn helps us with data visualization because it can give colors or things that visually tip us off as to what's happening in the data. For our next venture into our plots here, let's go ahead and add a trend line with regression. So you'll see what this is when I implement it, but it's unique to Seaborn in that we can only get this without calculating it if we use Seaborn. We would have to calculate it manually in Pandas and then plot the line manually as well. So again, we're saying pull our data from the data frame that we already have existing in Pandas. Hit the wrong button. Let's go ahead and give our plot a title here. It's going to be very similar to the one we had last time. Okay, and then when I run this, here we go. So it looks like there's just this line interrupting all of our data, but what it's actually telling us is if there's any form of trend. So this might not be the strongest case for regression because if you look here, you can kind of see the data is very scattered. There isn't necessarily a trend, but if we were to try and draw a trend from that, we would say that as memory usage increases, CPU usage, well, actually, no, that's not true. No, that is true. As CPU usage increases, memory usage decreases. So that's just kind of a quick glimpse into what might be happening, but this trend line in particular, you can tell might not be the strongest case for this data because the amount of spread that we have here is pretty high, and the number of points that fall in line with our confidence interval, which is how confident we are that the data will fall in this amount, is not super high. There's a lot of data that exceeds our confidence interval there. If you want to learn more about confidence intervals, I would say take a statistics class because they go into that very heavily in statistics. But yeah, this is a good starting point if you think that there might be a trend to a piece of data and you want to just track it and see if there is anything there. And that's kind of the gold mine with data analysis, is sometimes there is something there and sometimes there isn't. But either way, if you can uncover a trend, it will greatly help you determine what might be going on in the data. And of course, there's the concept of correlation without causation, right? So two ideas might be related, but one might not cause the other. So just be aware of what you think your data is trying to tell you and making sure that that is accurate. But anyway, if you had data that this would be useful for example, maybe like an age of computer to amount of time that a computer takes to boot an application, which I have seen in certain data gathering situations and systems. Usually we do see a trend where as the device gets older, it takes longer to boot and to run softwares, right? Which just makes sense. We know innately that that is possible and even likely. So you could use a regression line there to show that there is an overarching trend that is evident in your data. For this next one, we're going to take a look at the Pandas version first and then the Seaborn version of the same graphs, just so that you can see kind of how much work Seaborn is doing for us. So let's start with a Pandas bar plot. And I think we might have seen a bar plot, but just in case, we're going to take a look again. And while we're at it, we're also just going to add an extra manual aggregation. So sorry, also this is a string. Let me add that back in there. So here we are. First, we're calculating the mean. So we're not doing it to the same level as like calculating the mean for ourselves, right? It is automated. So Pandas is calculating the mean for us, but we are having to tell it, okay, go ahead and calculate the mean on a different line from our graph here. So now we can make the graph, which is our plot here. When I run this, oh, it didn't like it. Oh, future warning. Okay, so it's just saying that this will be deprecated at some point. But when we give this a quick shot here, you can see we've got healthy, warning, and critical. And they're all looking pretty similar. I mean, you can see there's a slight height difference between warning and critical and healthy, but it's not that dramatic. But it does show us that there's a slight difference, which, again, a big part of data analysis is just asking questions and seeing if those questions lead you anywhere, because sometimes they do lead you in the direction that you need to go and sometimes they don't. So you got to just take what makes sense and leave the rest. So this is what we're seeing. But notably, we can see that this is the mean, right? So this is on average what our devices look like. And now let's go ahead and do this in Seaborn. And as you see these side by side, you can kind of see the difference in the way that they're structured. So for example, they're comma separated here. And you also don't have to do this the way that I'm doing it. You can put them all in one line at the same time. I just like to separate it by commas because it can, well, Jupyterlab can correctly assess where there are breaks, and I find it to be easier to read for me personally if I have each argument on a separate line. But again, totally up to you. Doesn't matter. Space them as you like. You also, if you're used to having like all backed up like this, you can do that. You don't have to space them out like this, but again, for human readability, it makes the most sense to me to space out what I'm doing there. So we're looking at health status, CPU usage percent, And now let's tell it to use the mean as our estimator. So, whoops. We're not going to calculate it. We're just going to have it do that for us. And as you can see, we also didn't store the mean here. So even though we did calculate the mean, we aren't pulling that here. Seaborn just already has the mean for us, which is nice. We're going to give it the same labels that we gave our pandas, because it's the same style of graph. Oh, whoops. Ran a little too quick. These are just for the layout and then telling it to show it. Well, it looks like it did show it. So, oh well. We run this. Here's our big reveal. Wow. So you can see we've got not only healthy, warning, and critical, but we've also got our mean here. We're using that as our estimator. So it adds the error bars to show like the uncertainty that we have. So I misspoke, but basically that's, again, our interval. And it's showing the confidence intervals by default, which again is a pretty basic concept in stats. And like we saw with pandas, you'd have to do that yourself and manually draw the error bars. So we aren't given those error bars automatically here. And you can see they're just a little bit stylistically different. Like I've asked it for the tight layout. So it's kind of narrowing in that data more so than here. But yeah, as you can see, it tells a little bit more of the story with a little bit less of the work. We've already taken a bit of a look at Seaborn versus pandas and how they can be advantageous one over the other, but I want to do one more example that will convince you of Seaborn's strengths, and then we can go from there. So to start, let's make a grid. And this is going to return type facet grid, and we'll see why. Now, a lot of the documentation examples for this use G for the word grid, where I've used the word grid here. You can call it whatever you want. However, I think that grid is a little bit more explanatory. So if you're looking through the documentation of Seaborn, you might see G, but I'm going to call it grid. And we've used single character variable names like X and Y, but the only reason I used those is because I felt like they were pretty self-explanatory given that we are using the X and Y axis. We're almost there, so let's go ahead and show this now. Oh, there we go. Okay, so it took us a minute, but you can see there's a big variety of data here. And let's see if I can zoom in a little bit here. Oh, I can, but okay, well, it doesn't want to let me, but that's all right. Oh, there we go. So this is kind of the sweet spot, but you can see we have all the different hosts and their uptimes. So this is a more complicated question because we're looking at the amount of time that a host has been online per day and the days, which is pretty interesting because you can see there's a significant difference here. Now, that question of how would I measure the uptime hours over time split by host is interesting because it gives us a chance to figure out what is going on with our hosts. And you can see the names or the dates are a little bit jarbled here, but I think they're supposed to be spread out throughout. But anyway, yeah, this more complicated question is much easier to do in Seaborn than in Pandas, because in Pandas I would need to find ways to write loops, manage the axes by hand, and keep track of subplot indexing, which is a lot more complex. So if you're looking to answer more complex questions quickly, I would definitely recommend Seaborn as a tool. Now I'm going to go ahead and reset our stuff here. But yeah, quick little introduction to Seaborn for you. Now that we've covered relational plots, scatter plots, box plots, bar plots, regression plots, you name them, we're moving on to some other required visualization skills, which are categorical distribution plots, frequency plots, fold distribution plots, and plot enhancements. These are going to help us analyze how different system health behaves in our data set in our case. And more importantly, it's going to help you gain the skills that you need to visualize what goes into a good data set and what questions you need to start pulling from your data. So first, let's take a look at two categorical plot types that you haven't used yet, the count plot and the ViolinPlot. So the count plot is going to tell us how often each health status occurs. Let's go ahead and type this out right now. And again, we're going to hit it with our Pandas data frame. We're going to use health status again. Actually, I take that back. I just need this. And then... So we're only comparing two things that our data inherently has. Well, one thing that our data inherently has, and then the other thing is a count of what our data looks like, which I'll show you here because I don't know that I explained that perfectly, but... So that's our health status. That's what we already have. But now our Y label is the count. So this is counting how many times each health status comes up. And then doing that tight layout again. And we're going to show it just in case, because sometimes it doesn't show up, which is kind of wonky. And I don't really know why it does or it doesn't. But anyway, we run this. Look at that. So we've got a lot more healthy devices than warning devices, and we've probably got almost double the warning devices to critical devices. So you can see right away how this gives us a different insight into the data, because we didn't actually know, like looking at this distribution of data, you might be able to see just from looking through it that, yeah, the majority of them look healthy, but you don't know just how big that cap is, or the space between a healthy device count and the warning device count. So this is really good if you just need a quick insight into how many devices are actually having issues right now. One more thing, technically you don't need to add the title or the X label or the Y label, but for your sanity, the sanity of the people around you, and the quality of your work, I'm going to say that those aren't optional. They technically enhance your visualization, but you really need them. I mean, if I were to take count away and you couldn't see that, what would you think that this is about? Sure, it says frequency of health statuses, so you might be able to guess frequency, meaning the number of times that it happens, if you have the title. But if I took everything optional away and I just had X here, it wouldn't use it as a label. So we would have no labels on anything except for the health statuses at the bottom. And that would be much harder to parse than just being given our X's and our Y's. So try to be aware of what it is that you are saying with the visualization that you're offering based on your X labels, Y labels, and what you're asking of the data. Now let's go ahead and move on to a ViolinPlot. The ViolinPlot shows the full shape of the data distribution, not just the median, which we see in our box plots. So this would help us with, in this case, the question I have, does critical health seem to correspond with higher CPU usage? We were talking about that earlier, and the idea of causation and correlation and whether or not two ideas are linked. So let's go ahead and take a look at this. Oh, also notice the larger font size here, which is good. Oh, okay. But to have that set in stone, I'm going to go ahead and set the style and the context, which I believe we already have the style that I want going here, but I'm going to show you how to do it in case you want to change the style to something that you prefer. Maybe you work in an IT setting like me in the dungeon and everybody likes to work in the dark. And that means that if you show them this screen, you flashbang them. So you don't want white grid, you want something in black, right? In this case, it's easiest for us to see on a white background. It's best for our visuals, but do what you think is right based on the current aesthetic and needs of your report. So we're doing white grid, and then we're gonna set context for talk. And what that means is we are making the text larger so that it's easier to read. Once again, we're going to look at our health status. I feel like health status is a good question to be asking about because health status is an indicator of a lot of different factors. Like it's the most overarching factor of all of these pieces of data that we're being given. So it's good to compare it to other things in our data because it feels like the most comprehensive piece of data here. And now we're going to do our usual enhancement here, which is a title, although again, not really an enhancement. I would argue you need this. And here are X labels and our Y labels across the X and Y axis. Full disclosure, I can't see my hands right now, so I'm just going to write % instead of finding the percentage sign, which is why we're doing it differently this time, in case you were curious from previous times. It's on my keyboard right now. In my keyboard tray, I should say. So when we run this, there you go. Now, this gives us the density. So when you see a wider part of our data, that means that there's more data points falling within that range. So like our most frequent areas are right in the middle, right? Which makes sense. Because if you think about like a bell curve or the way that data is typically distributed, it's going to be more frequent towards the center and then oftentimes less frequent at the two extremes. Not that it's always that way, but oftentimes data does tend to look that way. I know we've already spent a lot of time understanding what a box plot looks like, and truth be told, this is a very similar layout to a box plot. So the thing that you really need to understand is that a ViolinPlot does a better job of showing the frequency of a particular data point. So if you had maybe like critical devices had a ton of devices happening at the 40% mark, you would say, oh, it's really weird that that's happening so much. I wonder if there's some program that's eating up roughly 40% of the CPU, available CPU processing power, and it's impacting the device health overall at the same time. So if you were to see something that was super frequent at a very specific data point, that might tell you a little bit more. I would argue that, and this is just personal opinion, but the ViolinPlot is maybe a little bit less clean looking than the box plot. So if you don't find any major conclusions from the ViolinPlot, it's better to use the box plot. But if you do find something significant, then it can be really good. And as you can see, it takes all of 2 minutes to run this. So you can get a very quick insight and decide, do I prefer this to the box plot? Is this something that I want to take or I want to leave? And then you can make it a decision based on all of the information. Let's go ahead and make one last histogram, which I know we did with Pandas, but we're going to go ahead and do it in Seaborn so that I can show you how to save your figure. So to start with, let's go ahead and make our plot, which is going to start out just the same as any other plot. And again, we're using CPU usage %, just because it's kind of an easy, statistic to look at. We're going to give it this. Now, I knew what KDE meant before this. It meant, like, basically it means that it creates a smooth curve over the top of our histogram, which represents, basically it represents how likely each thing is to happen, but I didn't know the name of it, so I looked it up. And in this case, it's called kernel density estimation, which is what it stands for, which is very useful for us when we are assessing how common something is and how often it shows up. I also realized I forgot to talk about something that I did earlier, which is here, which is share Y. So that means don't allow these to share the Y-axis. Don't allow some major overlapping that would make our plot basically unreadable. So sorry I forgot to mention that before, but now you know. We're going to do our same type layout. And now we're going to do plot.savefig for save figure. We're going to give it a name. So I think I'm still going to, well, I do like to keep my titles all one. I'm old-fashioned that way. I don't like spaces in my file names. And then I'm putting the name of the data set that I'm using because I have multiple data sets that I could be pulling from. So I'm just quickly mentioning what data set it's from. Oh, but I also need a type. So I'm going to do a PNG in this case just because they save well and they usually show up pretty well. And then we're also setting a specific DPI. So DPI stands for dots per inch, and that specifically refers to the resolution of the plot that we're generating, which in this case is relevant because we're thinking, oh, we're going to save this image and we want it to be as clean as possible for our boss or whoever's going to be looking at it. Now let's save this guy, or sorry, we already saved it. Now we're showing it. So let's run that. And there it is. Which is good. So you can see our distribution here. Everything seems to make sense. And you can also see our trend line there, which again has kind of a bell curve shape to it. So that's what we would normally expect in a lot of data sets. But yeah, this is good for us to save so that we can pass on, and it's pretty clear and easy to read. So to me, this is a successful diagram and something that I would be willing to share with the people on my team. So if you're like me, you might be wondering, where did my picture go? Because I saved the picture, but I didn't see a little download pop up. I didn't see it go anywhere. I didn't get a visual cue that it downloaded. And the answer is it did save, but it didn't save to your device. It saved to Jupyterlab. And here it is, right here. So if we take a look, here's our image and it's nice and big, which is good for us depending on what you want to use it for. So try to be conscious of what you're using it for and use an appropriate amount of processing and resources to make the image look good for whatever context you're using it in. For example, if you're using it in a PowerPoint, you're going to need that picture to be better at higher resolutions and do well in the larger format. And then if you were to use that same image in a Word doc that you were handing out during this presentation, you would also want that to be at a different size while still being viewable. So just be conscious of the format and the form that you're going to be giving your image to your readers and consumers of your data when you give it to them. Anyway, that being said, we covered so much today. Good job. And I know this is a lot to take in, but for the most part, we talked about different forms of data visualization, which is kind of the most fun and fastest way to glean something from your data as possible. And it can definitely kind of open new doors for you as you see your data out and see how it's supposed to be. And that is super helpful. So I would recommend taking a look at all of the different Seaborn visualization techniques because we definitely didn't use all of them. And there are more Pandas techniques as well that are also good. And I would suggest checking those out and reading the docs and just seeing how you can best use them and pull what you need from the data. But anyway, it's been super fun teaching you about this, and I'll see you guys later. Hi, and welcome to the third video in a 3-part video series about data analysis and Python. Today, we're going to be talking about data analysis and the life cycle of data. I'm not going to lie to you, it's going to be a bit of a doozy. So we're going to learn how to pull data from different sources, how to clean and prepare it, perform some analysis, work with some time-based data, and hopefully build some predictive models using linear and multiple regression, which I know is a lot of concepts. Like I said, it's kind of a doozy, so we're just going to jump right into it and get going. Now, before we really analyze anything, I want to make sure that we know some different ways to pull data. If you watched the first or second videos, we took a look at this code and I explained it in the first one, but to give you a brief synopsis, what you really need to know is that this is reading in a CSV. Our CSV is here, and CSVs are comma separated value files, and that is the format of data that I see most commonly. Generally, when we transport data, it comes to us in a CSV because we know what to expect and we know how to process it when we see it. So I suggest becoming familiar with this CSV parsing technique. And then I also want you to note that we've sorted by status, which is significant when we're working with our data because I have asked it to analyze those different statuses and take a look at what data can be sorted into those. And where are we pulling those statuses from? Right here. So it's already in our data, but we're telling Pandas, hey, this piece of this data has significance, go ahead and take a look. And then on the second line, that's where we're actually telling it that the categories also have an order and pay attention to that order because it's significant. Really quickly, I want to add in a couple more imports here because I like all of my imports up at the top. So let's go ahead and import JSON here, which we're going to be using soon. When I say soon, I mean in the next couple minutes. And let's import SQLite. People can be kind of elitist about how to pronounce SQL. I'm not here to tell you how to pronounce things or how not to pronounce things, but we will be using all of these, so know how to read them, and hopefully you can forgive me if I did not pronounce that in the way you prefer. But let's not waste time, let's get straight into it. So we've got our CSV read in, but let's say that I want to read some JSON. Well, I've got a JSON sample here, so I'm just gonna nab that and pop it over here. There it is. And now I'm going to read it as JSON data, which I'm not really expecting to use too much of, but I want it to be available and I want to make sure that we're distinguishing, between the different data forms. Now, I don't know where you've seen JSON or if you've seen it, but personally, I feel like I see it a lot of times when you're pulling data from the internet. So not like in a file, because people still put information in a file, but I've had it explained to me as like, it's kind of a way of flattening the data and making it easier to process in a web format. So now we can go ahead and run this. Oh, it didn't like it. Oh, future warning. It's deprecated. Yeah, okay. You let me know when it's actually deprecated. Sorry. Kind of a silly thing, but yeah. So now let's read in a stata file. So next I want to talk about stata and how to bring in some stata data. And if you have any complaints about how I'm pronouncing it, you can yell at the devs because I went and watched a video from them talking about their technology. Anyway, I don't want to take too much time up with creating the data, so I'm going to go ahead and just copy paste in some quick little data. Whoops, didn't mean to do that. And then I'm going to pull that baby data and make it work with what we wanted. And now I have a file named data here. So I'm going to send this to my data file. Basically, all that we're doing right now is we're making a file that we can then pull from and see how to pull from it. And here's how we would read that. And again, it all starts with Pandas, right? So Pandas is, even if it's not our first choice for data visualization, which it can be, depending on what you need it for, it is absolutely necessary a lot of the time for the processing power and the way that it can handle all sorts of different data. Okay, so now we run this and we get that same style. And you can see here we've got 1, 2, 3, and 10, 20, 30. And we're looking at an index here. So that's why this is 0, 1, 2. And then our X is as expected, 1, 2, 3. And our Y is also as expected. And so that's how you would import that. So on to the next, we're going to pull from a database, which would be SQLite, which is common if you have a pre-established database or some form of database management, and they're not just providing you with raw data that you are exporting. So this is useful if you want to pull directly from that database. Let's see. Let's do something similar here where we just kind of breeze through our data real quickly. So I'm gonna nab it and toss it out here. And again, it's not really coming from any particular form of inspiration. I just thought for a minute and thought what would be useful and what's quick, and we can just kind of toss in here. So now we're gonna connect. So now we can go ahead and read this guy back in. Because first we wanted to connect. Even though it looks a little bit convoluted, this is the process that we would use to read in from an existing table. Whoops, this is caps because it's SQL. Select wildcard, so select everything from our system table here that we've created. So read it all in, and then we can close our connection. Oops. And let's see our demo. Oh, didn't like it. Okay. Why didn't we like it? Oh. Because I'm being a silly goose. I had a feeling that this might cause an issue, but I just wanted to give it a shot. Okay, fine. I run you here, and then I run this. Pandas can also connect to real databases and run SQL queries or pull the results into the Dataframe. So we're going to go ahead and use a teeny tiny in-memory SQLite database just to demonstrate our process. And then you can replace that connection with a real server if you end up needing that. But for now, I'm going to do the same thing that I've done before. Except first I'm going to connect. I'm going to create a connection, sorry, which I'm just going to copy paste. I have that previously. Don't need us to take the time to type everything in for these because we're just doing the setup here. This is creating a little sample of our data frame. And this was us creating our SQLite database. And then now we're going to store this in our database as a table. And now let's do the part that's relevant. Let's read it in. So here's our SQL data frame, or SQLite in this case. Okay, so let's go ahead and run this, see what we get. And there it is. We have a teeny, teeny, tiny set of data here, which is good for us if we're wanting to just play with a small data frame, and we can take a look at how we import that data. The next concept that we were going to talk about is how to clean the data. So data almost never comes exactly as we want it, right? Usually there's something that we don't need, or we're missing values somewhere, which I've already told you how to check for missing values and make sure that everything is as it should be. But let's say that we maybe didn't want all of the fields that we had on hand, right? Like maybe we don't need uptime hours, or we didn't need memory usage percent. I don't know, whatever it is that we don't need, let's say we want to leave it out. Let's simplify our data frame, which you don't have to do this way, but it's easiest to do it this way because we already have an existing data frame. However, if you didn't already have one, our little representation of our data here is important because if you ever find yourself needing to pull from or use a database rather than a CSV or this form of content, then it makes it a lot easier for you to pull your information. So just keep this in mind and the structure in mind if you find yourself needing to pull from a database. But personally, I prefer to use comma-separated values and just export my information just because it's a bit easier for me to process it that way. But if you already have a good hand on database usage, then that might be best for you. So just do what works for you, and something to keep in mind. So now let's get into simplifying our data. I like our data set, but let's say that I didn't like it, or I thought that there was too much going on in our data set. I could simplify it by creating a smaller database, or by pulling, or not database, sorry, a smaller data frame, or by just pulling less data from our CSV in the first place. But since we've already pulled some data from our CSV, let's go ahead and make a smaller data frame. And so now I'm just going to write out all of the things that I want to keep. So like, let's say I want to keep the date and the host name, and OS might be relevant, so we'll do OS. And let's say health status. So I'm leaving out all of the real juicy bits of the data, but let's say that I just wanted to get an overview of all of our devices. I didn't really want to deal with everything else. If I give it what I want and I run that, you can see it's just showing us what I've asked. So it's pulled the new stuff out of our original data frame, and now it's just showing us that, which gives us a good simplification of what we had going on. And then in the first video, I believe, we briefly went over missing values, but we can do that with this if we want. Just quickly. So this is If there isn't anything here, give me a sum, like add 1 to your total for each of these. And then at the end, tell me how many of them don't have a value. So in our case, all of them have a value, which is good. That's what we want. But if you ever see a number higher than 0, when you run this, you know that you are missing a value. So I'm going to go ahead and do something that will, strangely enough, add outliers back in so that I can make a point. So to start with, we're going to add in our CPU usage percent back into our simplified data frame here. I'm doing that because we've seen in our previous video that there are a lot of outliers in this particular section. So now I'm going to go ahead and run that. And you can see CPU usage percent popped up. But now we can simplify this. So let's cut off all of the things at the very first and 99th quantile. So the very highest outliers and the very lowest outliers are both getting cut. So we can see the highest high and the lowest low, and now we're going to take these and say, just replace the current data frame that we had with our new data frame that is without any outliers. Now, I would argue that in this situation, you might not want to do that unless you're taking like a mean or a median and you're trying to see, well, really a mean, because outliers don't cause so much of an issue with a median, but with a mean, when you're adding everything up and then dividing by the number of values, it can cause issues if you've got massive over or under values, I guess, things that are way above or way below what you would expect. And so if you're doing a mean, then this is necessary, but otherwise I would argue that you should be careful, because when you take data out, you aren't looking at that data anymore. So if it's an outlier for a reason, like if it has crazy CPU usage percent and it's critical and we're still looking at critical devices, then you might want to hold on to that device and maybe not overwrite your data frame. But here we're just doing a little example of how you can clean it up if you needed to. So just something to be aware of. Maybe be cautious when you clean your data like this. That is not an integer. Okay. So now if we run this, oh, it didn't like it. Why didn't it like it? Oh, my mistake. Okay. Now do you like it? Oh, okay. So, oh no, we've hit an error, and actually this error comes up quite a bit. So what happened with setting with copy warning, it is telling us, Pandas is telling us, hey, this might just be a view into another data frame. It might not be a completely separate copy. So if we want this to be okay and definitely not mess anything up, we need to go ahead and change how we're doing stuff. So if we want to fix it, we're actually going to go back and go to where we first had the issue, which is back here, because we didn't necessarily make this a copy. We said, go ahead and point to data frame and take these things away. And so now Pandas is unsure if we're saying that simplified data frame is a view of data frame, or if it's actually meant to be something separate. So to handle this, we're going to go ahead and turn simplified data frame into a copy by using .copy, which is a function that does exactly what it sounds like. It makes a copy. So we run this guy, we run this guy, we run this guy, and now it doesn't complain. So now that we've cleaned this all up, sorry, I'm going to go ahead and pull something that we did in the past video and create a ViolinPlot here. So let's just really quickly, or sorry, not a ViolinPlot, I said that, but a box plot. So we're going to pull from our data frame. Except in this case, we're going to use our simplified data frame because it wouldn't be any different if we used our current data. Okay, and then in the interest of time, I'm going to leave out, oh, that's okay. It wants me to run my stuff here, which it's right. I'm realizing that I forgot to import Seaborn. There we go. So now I can run this. Just keep running it down until we get to here. And there you go. This is... So let's talk about apply and lambda expressions. You'll use them for custom transformations. It helps you create flags, categories, and derived features for your analysis and modeling. And lambda expressions are pretty much everywhere in Pandas code. So let's take a look at how we go about applying that. And to start applying anyway, to start with, let's go ahead and create a named function and then use apply. And if you see here, it looks awfully similar to just a regular function in Python. So we're looking at a single value here. And it's specifically for CPU percentage, which I didn't make super clear, but yeah, we're looking for the current CPU percentage and we're trying to categorize them. Not 96. Close. Okay. So now we have this function, right? And we're going to go ahead and apply this categorization to our data frame. So what are we doing here? We're saying go ahead and apply this function that we've created here to our data frame. Now we're going to print it to see what it is. And to do this, we're using our print statement, but we're also pulling the value counts from our data frame. Oops. And when we run this, you can see we get low, medium, and high. And okay, so yeah, you can see all the different categorizations and you can see it's sorted it by the number, right? So we've got more medium CPU levels than high and more high than low. So let's say that we need to do something quickly and we just need to apply a function, but we don't necessarily want to do this whole process of writing out a definition of a function and then making it so that we can call back to it whenever we want. We just need something quick and dirty that processes our data. So let's do that by computing the square of the CPU usage. So it's not quite the same, right? Because we need something that can be affecting the data not necessarily sorting the data and making a decision about it, just impacting it in some way in order for this Lambda function to work. But let's go ahead and do that. Oops. And again, they're important because you might want to use a more condensed or shorter application of your function. And if you don't want to go through the process of defining a function and all the normal function steps, you might want to consider a Lambda function. So here we're saying apply. Go ahead and apply this thing. What is it? Lambda of x. What are we doing to x? Whoops. X squared. How we would expect. Okay. And then we can't really, I mean, it's going to accept it and say, oh yeah, sure. But we don't really know what it's doing here. So let's go ahead and just preview what it did. I keep capitalizing CPU usage %, but it's not capitalized, which makes sense, but blah. Okay. CPU usage %. Again, we don't necessarily need to list everything. Memory. Okay. Anyway, sorry. And then normally for readability, I would space this out more, but since we're just kind of taking a little peek at it, I think it's fine. And then we're going to pull the head, which, as you know, is just the first few rows. And what do we get? Oh, it didn't like it. Why didn't it like it? So to do this, I'm just going to pull what we did, and I'm going to, let's see. Got our nested here. Then we're going to do CPU squared because that's what we just did. And then we're going to pull the head. So the first few rows, as you know, and there it is. Now those are really big numbers, which makes sense because we were squaring numbers that were already decent size. So there you go. And I'm not sure why you would need to square all of these, but in case you need to do a quick mathematical operation on all of the items in your data set and add them to a row or a column, you can do that this way, and it's pretty helpful. So now I want to talk about a pretty important subject, which is how you would combine or merge data frames. It's pretty important because oftentimes data is split across multiple tables. Think you might not have access to all the data from Microsoft Azure while you're working in an Apple environment, or, you know, different applications and different areas collect data on their own. And we need to be able to merge our data's tables so that we can make sure that we have everything that we need. Pandas makes it really easy with the merge function, which looks a lot like a SQL join, if you know what that is. So I'm going to pull another data frame, and I'm not going to take all the time to type it out because it would take a minute. So let's just nab a data frame called host metadata. And if we could just run with this, let's go ahead and show it. There it is. You can see it's got everything that we need. And now we're going to merge this. So the department and the machine type and all of that is being merged by host name because that's what we have on our side, right? So not medac data, metadata. So we're starting with that table that we made. What are we merging it on? We're merging it on the host name because that's what they have in common. And actually, I do want to have these be... Oh, it lost my O. Okay. And then how? We're using left. So we're merging on the left. Okay. And now... There you go. So we can see on the left, we've got the date, the host name, the OS, the health status, all of these things look an awful lot like our first data set and CPU usage percent. And then we've got CPU level. You can see it's got things from each area, right? We've got finance and the machine type. So it's successfully merged those two databases that we wanted to merge. And then the next thing we'll talk about is long data. So far our metrics have lived in separate columns, but it can be easier to see when you group them into the long format, where each row says at this date for this host, this metric had this value. So instead of trying to play them off as all separate, like we see here, where they're all listed separately, we can do this the long way. So to start with, let's go ahead and do a melt, which melt is going to convert data from the wide to the long format. So let's make a long data frame. We'll keep using our simplified data frame. And the variables we're going to use are date and host name. I hit enter too quickly by accident. This is the name of the new column that's going to hold the metric names. And this is the name of the new column that's going to hold the metric values. Oh, missed a comma. Boop. Okay. And then let's go ahead and preview that. Oh, it didn't like it. Oh, I guess it's because I didn't add this to our simplified data frame, which is okay. We can just do something different. Let's do health status. So to start with, let's go ahead and make a new data frame, our long data frame. I'm going to say pandas, go ahead and melt this. What are we melting? Our data frame. Except I. So these are what we're unpivoting. So we're taking them down basically. Whoops, but I need my comma. No. And this is for what we put at the top of our columns. Now we can close this guy off. Let's just preview our long data frame. And there she is. Doesn't look that much different but what if we go ahead and create a line plot just to see if it creates anything different for us? Oops. Or anything like that for a report. But in the interest of fun, I will call it what I want for now. And let's see what we got. Oh, I didn't like it. Are you sure? Oh, yeah, it's because my imports aren't here. But that's okay. It did find it, so not all of it. It didn't like this, so we didn't get it. But yeah, if we had put in the plot here, then it would just give us the title. But either way, you can see that this is our one line per metric over time. So being able to make the data long can help us in the way that we process and group our data, basically. And it's important because you might need to plot both of the metrics with the same code. And because each line represents the one metric, we can compare how they change over time more easily. So next we're going to group and aggregate our data. This is helpful to us because it helps us summarize our data across categories. So for example, I might wonder, what's the average CPU usage for each health status over the course of all of our healthy devices? What does our average CPU usage look like? This can really help us with our descriptive analytics and determining how we want each category to look, or how it actually does look based on the shape of our data, and also what story we want to tell based on that data. So let's go ahead and jump right in. Take that back. I don't want to use the simplified one for this. I want to use our main data frame here because I think it will help us visualize this better. Oh, and now for this, we're going to pull the mean from our mean function. There we go. And then we're going to display it. And it gave us a future warning. Oh, we talked about that before. So we're going to skip through and look at this. And you can see for healthy, we have a CPU usage percent on average of about 45%, and the warning is 44, and then critical is 45. So that has told us absolutely nothing about what could potentially be happening, because it seems to decrease, or it seems to start here and then decrease and then increase from the original, but very slightly, not enough that I would call that a significant difference. However, if we look at memory usage percent, you can see that it has increased by 10% from healthy to critical. Now that might not be a huge amount, but we do notice a trend where it's consistent the entire way up. And I'll also say that 10% can be make or break, and it suggests that perhaps something is going on in the background that could be causing other issues. So if you're a good technical worker and you have a good eye for this kind of thing, even just seeing a small trend like that can be very telling. And that's what makes grouping and aggregation important, is that it allows us to really see what our data looks like over larger trends than we could maybe see just from scrolling through this, right? I wouldn't be able to scroll through all of this data and say, oh, you know, there's a mean of 45.5 CPU usage percent for healthy devices. I'm just not going to know that. So yeah, that's what makes this pretty good. The next thing we're going to look at is pivot tables. So pivot tables can help reshape the data like Excel does. So index versus columns and aggregated values inside. this is important because it gives us the ability to do something very similar to what we see in business reporting. So we see this type of data in a lot of business reporting, and if you happen to use Excel a lot, these tables will probably feel more familiar. And if you're giving this to someone that is a businessman or a businesswoman and they tend to prefer Excel, then you might want to give them a pivot table. So let's go ahead and create one. I'm going to be very creative in my naming here and name it pivot table. I'm just going to check our naming convention for... Oh, I'm glad I checked it. It's not device name, it's host name. Okay. Oh. For our pivot table, I'm going to go ahead and call back to one of our previous charts, in this case, our merged data frame, because I feel like it will be helpful for us in showing the variety and how a pivot table really looks. We don't have that many factors for our regular data set. So, oops, I don't know why that's like that, but... So what are we doing here? We're using the numeric value that we're summarizing. We're choosing one here, which I want to do CPU usage percent because we've been working with that a lot. We're going to use the department as the index because we're asking the question, sorry. We're asking the question whether or not CPU usage is different across departments, and then we're wondering if health status plays a role as well. So here's our department. Use health status for our columns. And then what are we computing here? We want to compute the mean. And then if we happen to find, we know we won't, but I think this might be useful for you. So if we happen to find a value that has nothing in it, if there's not a number or it would crash, just replace it with a 0. Now let's display our pivot table. Okay, well, we got another feature warning, but that is okay. And what do we see here? Oh, well, okay. So when it comes to IT, it looks like IT has the healthiest computers that are healthy. So we have the least CPU usage percent in our healthy IT devices. However, it's looking like IT has the second highest CPU usage in warning and also the second highest in critical. Now, we noticed that finance has the highest on warning and critical sections. Even though they aren't the highest in the healthy status, that leads us to believe that it's possible that they have some kind of CPU usage in their applications that's very costly. So it might be good for their IT technicians to check out what those potential problems are. So this type of pivot table can help us sort of look at what the issues might be and create our own answers about the data. Because I certainly, again, similar to the last grouped, right? I would not have been able to determine what the means of these health statuses would look like based on the department. Next, we're going to take a little look at time series data. So what is time series data? Time series data is any data that's indexed by time. So for example, logs per day. Pandas can treat dates as an index, and then they can fill in any missing dates with reindex, aggregate them into weeks or months, for example with resample, compute rolling averages, and compute cumulative totals. This matters because you're going to want real monitoring using largely time-based data. You may also need to answer questions like, what's our weekly average for CPU usage? Is it trending up? And how many high CPU events have we had so far this month? So let's go ahead and take a quick little look at doing this over time. So this is our time data frame here. So we're going to make a new data frame so that we can impact it, just like we saw with our copy warning. We don't want that again. Which we should have already done this part, just so you're aware. We already converted it to a DateTime, but just in case you don't remember how to do that, we're going to do that, and then we're going to sort it. Okay, so now if we run this, let me take a quick peek at the head. It's telling us the date, and they're all from October 4th. So what are we seeing here? We're seeing all the different host names. So if you wanted to, you could take a quick little sneak peek and you could pull by dates, right? This is really useful for our grouping and if we need to see things in a chronological order. So we're going to talk about two concepts at once. We're going to talk about resampling and reindexing. So first of all, what is resampling? Resampling is grouping time series data into new time bins, such as weekly or monthly, and then aggregating that data. And now reindexing is when you create a continuous date index so that there are rows for every date or whatever interval you choose. So day, month, year, hour, whatever time interval you choose, it's consistent, even if some days were missing from the original dates. Now, we're not going to be able to reindex our data as it is now because, as you can see, we have multiple entries for the same date. So, well, I guess you can't really... There we go. We have an October 31st here, and we had an October 31st up here as well. So that means that we're not going to be able to index it. However, if we use resampling and then reindexing, we can create that continuous data set, which I do believe that our dates are currently consistent, but I think it's good to see just in case because real life data isn't always that way. It's not always that convenient and easy to use. So to start with, let's resample. So there we go. That's what we needed to do. And now let's check the head. Whoops, not namely. Gosh. Okay, and now you can see the average CPU usage percent per day for everyone. Now, I understand that this statistic might not be all that useful because we are just like checking the average of all devices, which is not that useful. But there are other stats that might be pretty useful for when you think about it, right? So if we wanted to know how many times people reported filing a new form or something like that, and you needed to know on average how many times an event happened in a day, that might be useful. More importantly, though, this opens the door for us to do our reindexing. So now we can say, let's find the full range of dates by looking at this Pandas date range. And we need to use that daily CPU that we just created. Sorry, I just said that and then anyway. Not date range. I need close, except not at all. We're gonna pull the head again, although realistically it should have pretty similar output. There we go. And there it is. And it looks exactly the same. But we could also have it print. Let's see. Let's have it print. Okay, let's see what that says. There we go. So the max for that is November 2nd of 2025. And the min, as we see, was October 4th. So that tells us the span that we had this over. We also would know if we had any missing values, it would let us know, but we don't, and we knew that going into it. But these are some ways that you can aggregate and work with your existing timestamp data and kind of get an easier look into what your data is saying. So next we're going to talk about a rolling window. A rolling window is a moving window over the data that computes a statistic. So it's kind of a moving average. So in this case, we can use that same CPU usage percent, to take a look at how it looks over the first few entries. So let's do our same timestamp data frame here. And let's do a rolling average over the first 7 entries, which seems kind of random, except I'm thinking about this as like, if you had an one after another, like regularly indexed set of days, then you could do this over the course of 7 days. So since I think that's a pretty common usage, we're going to go ahead and do it that way. But you can use however many you want of entries. This is where you enter it. Boop, just one little integer. And in this case, I'm going to ask it for the head, but I'm going to ask it for the first 15 entries. So when I run this, there we go. You can see our first 7 entries say, I don't know what that is. I can't do anything with that because I don't have 7 entries yet. So once we get to 7, it starts hitting an average. And you can see over time, there's not really a trend or anything. It just kind of, we've got 48 and then 52, and then it starts kind of balancing out a little bit here. But yeah, it's useful because you can see what the moving average over a moving window looks like. Now, moving averages are pretty useful, but another thing that can also be useful and an important part of your toolkit is a running total. You probably already know what a running total is, but it's a cumulative sum over time. So, for example, how many times have we had our CPU usage go above 80 in the month? And then just tracking that one event happening over and over and over again and that frequency and just having it tick up. So let's create a running total of that. Oops, I don't want to reassign this. We're going to do our cumulative sum here. Boop. Now we're going to show what we want to show. Couldn't get 8 there for a second. There we go. Oh, the classic blunder. Yeah, my bad. Missed a little something. For a second, I thought this was correct and it was trying to do a comparison. Anyway, I digress. There we go. So, in all of these entries, we don't find a single day where it's above 80%. And actually looking at our data, that would be correct. So I'm going to drop this. Even though the name is still going to be inaccurate, I'm going to drop it to 50 so that we can see it increasing. There we go. So now you can see it's not above 50. It's above 50 once, not above 50 for any of these. And here's 2, right? So it's just counting up all of the number of times that that hits, which can be useful if you need to know how many times something occurs in your data set. So we've come to the most conceptual and most topical topic that we're going to be covering in this video, and that is predictive analysis. Predictive analysis is the process of using historical data or data from the past to predict future values. So, for example, if you're predicting prices for people at grocery stores by guessing what they'll buy, or the weather forecast, all of these things use data and a variety of different factors to create a predictive analysis. We use them in IT for forecasting system load or detecting anomalies, or most importantly, preventing outages or failures before they might happen by predicting them. This is how we turn what happened into what will happen and start acting instead of reacting for what we think will happen. So to start with, let's go ahead and create a correlation matrix. These are pretty simple. I'm going to go ahead and use our simplified matrix because it's not too complex of an issue here, but I'm going to use numeric only because I don't want it to try and read in like health status and say, I don't know how to process that as a number, so I give up, which it will do. So this matrix is showing us how strongly each variable relates to the other variables. And a correlation close to +1 or -1 means a strong relationship, which can be helpful for our prediction. And if you look here, it seems very likely that they're related. But now we're going to move on to using scikit for linear regression. And scikit-learn is a free and open source machine learning software, and it's used in Python, obviously, primarily. It's built using other fundamental Python libraries that you already know about, like NumPy and matplotlib, which we've already used, and it can really help with using efficient tools for machine learning and statistical modeling tasks. So we're going to go ahead and get into it. And first, we're going to train a linear regression model on what we've already been talking about, so CPU versus disk free space. So first I'm going to import our model selection. Well, from model selection. And now we've imported these. Oops. Don't need two here. My bad. Okay, so we're going to split into training and test sets. So we need to train our model with data before we use it. Now we're going to go ahead and train it. And create it. Sorry, should have mentioned that. This is evaluating our model performance. So we're going to see how accurate it is based on the number that we get out. I have a feeling that it's not going to be great, but what's important is not that it's a perfect model. What's important is that you understand how it works. Oh, yeah. Whoopsies. Okay. So if we run this again, there we go. So now we got this teeny tiny number. a teeny tiny negative number, I should say. And what does that mean? It means that our model is actually a little bit worse than just predicting the average every time. So the relationship probably isn't linear, and it doesn't mean that your model is bad, just that the predictor that you've chosen doesn't really explain the target's behavior. So our predictor explains 0% of our CPU behavior, and using it actually is slightly worse than just throwing a dart at the average every time or like rolling a die. So there's no linear relationship at all between the variable that we chose and CPU usage, which the variable that we chose in our case here is disk-free gigabytes, which I guess makes sense. But now we know that that model is not going to make accurate future predictions. It's also super common, so don't feel bad about it. Next, we're going to talk about plotting a regression model with Seaborn. And a regression plot can help us visually confirm whether a linear relationship exists. So again, if you need to just see it, you can go ahead and look at it this way, which I'm pretty sure we talked about this, but this is now relevant to you specifically here. So let's go ahead and take a look. But we do already know that this isn't going to be relevant. So it's going to look like a whole lot of nothing, but it's good to stay consistent just in case. We are going to switch it up in a second though with a different example. Oh, forgot a comma. And then this is for our regression line. And let's go ahead and run this. And nothing. We talked about this earlier, right? I mentioned that, oh, see the spread on here? It seems like it's unrelated. So yeah, we got exactly what we thought we would get. They're not super related, but now you can see. So let's go ahead and make a simple regression model for a cars data set now. I'm going to go ahead and switch it up a little bit. And again, instead of creating an entire new data frame, in the interest of time, we're just going to copy paste one in. So there it is. There's our little cars data frame. And let's go ahead and take a look at cars. There it is. Boop. And now we're going to do a simple regression with just one feature, and that feature is going to be miles per gallon to weight. So I'm not sure if I already added these. Well, I added one of these. Actually, I think I added both of these imports in already earlier. So let's just get into it. Okay, then also we already have this, and I'm going to pull it again in the interest of time because you have seen it before. Is this going to be different though? No. So we went ahead and stole this from our previous model because we already have it, but it is going to look a little bit different. Okay, so now we're going to print this and we get nothing. There's no relation, as we talked about with the previous one. So we could see how it might use only weight to predict miles per gallon, which I would think it would have a slight effect on it, but very little, because there's a lot of other things that factor into it. But now I want to look at two factors. I'm going to look at weight and horsepower. So to do that, I'm going to come back in here. I'm going to say, anyway, to do that, I'm going to come back in here and I'm going to look at cars, weight, and horsepower. And it's going to look the same as the last one. So we're going to pull this, except now we're going to use our test size as slightly larger. So there's that. And if you're interested in linear regression and the idea of training a model, I would highly suggest reading up on it because it's a very complicated topic. And it's definitely accessible. Like, there's a lot of information on it. It just takes a little while to learn. Okay, and then when we run this, oh, it didn't like it. Oh, because there's a backslash. Anyway, there we go. Okay, so this number is not great, but it's a lot better than the previous one by like a full factor. Like, we've got 3% here, but we've got 1/8 of a percent, or not 1/8, sorry. 80% of a percent here. So this is definitely better. We're almost done here, folks. So the second to last thing that we're going to talk about is categorical variables. So to do this, we need to encode something that's not already a numeric indicator. And to do this, we're going to use get dummies. So get dummies will turn our origin column into a binary indicator. So one for European and one for Japanese, and this allows the model to understand categorical differences, which we did also do something similar with our health status when we made it categorical, but in this case, we are just assigning a 0 or a 1 because it's a binary indicator, or, you know, there are two options that it could be. So anyway, so now if we run this, you can see instead of having a value where it's Japanese, oh, sorry, not European. I said European earlier, but I meant US origin. Although we also have European origin, so that could be an issue. But anyway, I digress. You can see here, we've eliminated the European one, or ones, and we're maintaining, if it's Japanese, then we'll mark true here, and if it's of US origin, then we'll mark true here. So rather than a string, it's something that can be encoded. And finally, our very last topic for this video is how to improve a multiple regression model. So model improvements can come from a variety of things, like adding new features, or using nonlinear transformations, or removing weak predictors. But here we might add like weight squared. So for improving linear regression models, our data set for cars is a little bit small, but I'm going to give you some ideas so that you can pursue this in the future. And to improve your linear regression model, I would suggest starting simple, but then adding meaningful features and adding new methods of measure. So what you could do, for example, is you could start training your regression model on multiple different factors, or you can start adding in more predictors. You can start adding categorical features like we saw with our origins. In our case, we know that the origin of the car probably isn't going to have a lot to do with our miles per gallon, but if you were wondering like the processing speed of a computer and you were wondering what size RAM it had in it or something like that, it could definitely be relevant based on a binary system. So I would say just evaluate the variables that you have and start factoring them into your linear regression model. And that is the best advice that I have. But anyway, we've covered a lot of topics today, and I know this video was a doozy. So thanks for sticking with me and working through it. Today, we just covered all sorts of information about data analysis and linear regression. And I feel like, you know, if you have any questions about this, please feel free to go back and watch through them. If you're not understanding something, you might want to check the first or second video, but I'm glad that you came with me on this adventure, and thank you so much.